Thank you. It's a great pleasure to give a talk here on a topic that's dear to my heart, which is the connections between what I work on, string theory, and predictions for observable universe. So string theory is a consistent framework which tries to unify quantum theory with Einstein's theory of gravity. And this is a non-trivial accomplishment because many different attempts have been made to do this, and by far the most successful one is string theory. And the basic idea is replacing the point particle entities that we think or we thought were the basic building blocks of matter by extended objects as building blocks like one-dimensional strings or perhaps membranes. So higher dimensional objects seem to play a key role in making this work, the quantum theory and Einstein's theory to be merged. So the basic idea is very simple in terms of how the string theory describes physics. Namely, the main thing in physics is how particles interact with each other. And in the context of string theory, you basically ask a similar question, is how the strings interact, which means they join or go backwards, they split. In a nice geometrical pairs of pants diagram, as you can see, the shape it forms a pair of pants, and we say the pair of pants dictates the physics. So it's a very geometric way of describing what are the interactions. And within it, it gives you all the particles potentially that we know and all the kind of things that we expect from it, depending on the various details that we come up with. And so, for example, you can have one of these particles, which we want to talk about, let's say quarks. The up and down quarks, they could look like strings of one form, or they could be looking like either closed strings or open strings whose end is ending on some region and so forth. So there are different possibilities of how you realize individual particles that we see around us in the context of string theory. But one of the novel features, and perhaps strange features, is that it predicts the dimension of space and time. Before this, we thought it could be any dimension of space-time. You could just choose it, and we usually chose it to be the one we want, namely 3 space and 1 time. But actually, in retrospect, you might have thought, why 3 plus 1? Why not any dimension? And string theory begins to put an answer to that. It says, no, not every dimension is possible, but it's more than 3 plus 1, luckily, because it should at least be 3 plus 1. But the surprise is it's not like 10 billion dimensions. The dimensions are small in string theory, and we can have 10 or 11 dimensions and so on, but no more. And this is already quite amazing that we are predicting the dimension of space-time, and it's not too different from what we actually observe. But nevertheless, it's not 3 plus 1. It's somewhat higher. So we have extra dimensions, and we have to reconcile it. And the main way to reconcile it is that they better be small, these extra ones. If we have 10 dimensions, 9 space, and 1 time, you would expect that 6 of these spatial dimensions to be sufficiently tiny to avoid detection by experiments. And so you can think of it this way. So think about, suppose here I'm just denoting as if the space was 2-dimensional. You can have one large dimension, this along this direction of it, and the other one could curl up to something small like a circumference of this tube. And so if this is sufficiently small, you can hardly distinguish this geometry from just a 1-dimensional line. So whether you call this 2-dimensional or 1 dimensions depends on whether the circumference is sufficiently small. So this is just to illustrate, and if you have extra dimensions, you can imagine having these extra circles, which are sufficiently small to avoid detection. There would be no problem, and you could, in principle, deal with it that way. But exactly what is this circle? Does it have to be a circle or a product of circles, or what is the shape of this space? We don't know, and this is an artistic rendition of it. Don't take this too seriously, but the way I want you to think about this in this context is that the yellow lines here denote the large dimensions that we see around us, like 3 spatial dimensions. And at each point, you should imagine there's this other degree of freedom that you can go around, which could be complicated, like these shapes suggest. Somehow curved, curled up in some way, very complicated shape. We don't know the details about what shape is there to get. And again, the artist, drawing the dimensions in 6 extra dimensions is not trivial, so instead of drawing higher dimensions, you draw more colors. So, so this is just a cartoon, if you wish. Now, it turns out, though, you couldn't ignore what you choose as these extra dimensions. It turns out the details of what you get in our observed universe depends on, for example, the topology of these extra dimensions. Even though it may be tiny, the nature of the topology of it impacts what are the particles you see in the three-dimensional space at one time that we observe. So it's the details of that manifold in some form come out to be relevant, even though it's small. So we cannot say it's irrelevant, just choose whatever you want. No, it's crucial what you choose. And so we actually better study them carefully to know what are the space of all possible spaces that we can get. For each one of them, we get a potential solution to string theory equations, and whatever we get for that, we call it the string landscape. So the consistent choices of what you can choose as these internal or these tiny spaces, we call a choice of string vacuum, and what physics they lead to in 3+1 dimension, we call it as our string landscape, the landscape of possibilities in string theory. So here I'm just denoting an example that if the internal space had a donut-shaped object that we call torus, you can have, for example, a string wrapped around this one of the cycles around this like this circle here at a given point in the macroscopic in the observable universe. So it will look like a particle, even though it's wrapping around some internal directions. Or it could be, for example, the same point in space, but it could be wrapped around a different cycle in the other tiny thing. So it looks like a different particle. So these string configurations or these membranes or whatnot, depending on which configuration they wrap around or do, you get you different particles. Or they could be excited and oscillating in some form. They give you yet another particle. So they get a zoo of possible particles and all that, depending on what you have. And you can see that if you have particular cycles, each cycle gives you some kind of a charge that you can count how many times it's wrapping around here or there. So these give you the possibilities begin to be interesting. And so they have their imprint on the observed 3+1 dimensional physics. So this leads to a vast landscape of string vacua, and this is like a landscape. You can imagine this as a landscape. Each manifold you choose up there in terms of what are the possible choices that you do leads to a possible different universe with different number of particles and so on. So each point in this landscape, I want you to think of as a would-be universe. So this point is one universe, that point is another, this is one universe, this is the other universe, and so on. There are all these ones are different universes with different number of particles, different masses, totally different properties, all dictated by what was this internal space. Our universe is just one of them, somewhere there. We don't know exactly why it has to end up to be with that particular one, but if string theory is correct, we expect that one of these guys is actually the universe we live in. Now, going from choices of what are consistent internal manifolds, these tiny spaces that you can have, to what you actually observe around us, it's a huge number of choices. So therefore, it's cumbersome. And you might raise the opposite question. You say, look, you have so many choices. Why don't you pick the physics you want to see? You say, I want to have 5 electrons, 2 kinds of quarks, and this and that, with these masses. Let the string theorists worry about how to get it from some manifold. I won't worry about it. Just I start with something which looks consistent in terms of 3+1 dimensional physics. Somehow you can figure out, because there's so many manifolds you can choose, somebody will come up with a way to get it. That could be one attitude. Actually, it is vast. The string landscape is vast. But can you get any conceivable universe which looks consistent in terms of forces that we know in 3+1 dimension? Can you get anything you want that doesn't look inconsistent in terms of what we know about quantum field theories? And the answer turns out to be no. And that's the main lesson of string theory. That is, in fact, almost all consistent-looking quantum systems that you think about matter and this and that cannot arise from a quantum theory of gravity. So the set of things that you can actually get is finite, we believe. So there's a finiteness to it, which is a very restricted set, as opposed to an infinite set of possible consistent quantum theories, which we do know exist. So consistent quantum theories we know exist, but when you include gravity in the mix, it will give you restrictions, and therefore not everything can necessarily arise. And we want to know what distinguishes a good one from a bad one. So the good ones we call the string landscape, and the bad ones, which look okay but they are not okay, we say they belong to the swampland. This terminology was used not in recent history of politics. It's 10 years old terminology, so no connections. So almost no consistent looking effective theory can be coupled to gravity, as it turns out. And the ones that do are just jewels. They're just rare jewels that happen to be possible to get. So in other words, if you look at the space of all possibility, you might imagine this is this set, but actually the ones they're like a bunch of points of possible ones. And we want to know which ones, what characterizes these points? What is special about these points? How do we characterize this finite set? That's the program of trying to understand the string landscape and distinguishing it from what we call the swampland. Well, this is the swampland over here, for example. So we want to know what are the nice jewels like these trees. Now, actually, the best understood subsets of what are these spaces, instead of getting to a cartoon level, to the actual space, are the ones which solve Einstein's equation, which is what we call the Ricci flatness, and preserve a property which is called supersymmetry. So this is the best understood classes that we have in choosing what these manifolds are. And this is actually part of studying some of these cases that are possible among these special manifolds which are Ricci flat, is part of the Simon's collaboration on spatial holonomy in geometry, analysis, and physics, which are having actually a workshop in the past week and are continuing having it some conference here in the next 2 days. And let me list just some of their important recent works. But to do that, I first have to tell you what the word spatial holonomy means, at least a caricature of what it is. So if you have a space, like these tiny spaces I'm talking about now, and if you take a vector, and if you just move around as straight as you can, and you go around the loop and come back, if there was nothing curved, if you take a direction and you come back, the direction of that vector doesn't change if you go as straight as you can. So therefore, you would say that the vector comes back to itself unrotated, just the same way it was. But if the space is curved, like a sphere or something, as you go around different directions, even if you try to keep it straight, you come back, the vector gets rotated. And this is called the holonomy. This rotation is called the holonomy that you experience as you go around loops. It turns out not every kind of rotation can arise if you consider various manifolds. Just there are some special ones that can arise. The ones that actually arise and are very useful in the context of physics, one class turns out to be what we call the SUN holonomy. And these are these compact tiny spaces which are known as Calabria manifolds. These are very special ones which when you go around, the rotation group you get is a subset of rotation group which sits in this other group called SUN. But then there are actually a few more exceptional ones. So this is characterized by an integer, but there are two which are not, there's no indexing, there's just two choices. One is G2 group, and the other one is spin 7, which are very special. And it turns out they're both interesting for physics of the 4 dimensions. And G2, you might wonder why you get such exotic, complicated groups and how you understand it. Well, it's not easy to explain it, but if anybody wants to ask, I would suggest perhaps asking Jim Simons, who actually was one of the first people who actually came up with the classification of what are the allowed possibilities. So this has been known for a while, that these are the list of possibilities, but to actually understand what geometries they can have and what are the detailed properties to construct such manifolds and study their properties is still a work in progress, and it's a very complicated subject, and it's going to have deep implications in the context of these criteria we're dealing with. And so let me just flash some of the works that this collaboration is doing. So they're constructing new spaces which have these kind of holonomies, G2 and spin 7. They consider gauge theories, which are these forces that we deal with in the context of these special holonomy manifolds that they can have on it, as well as structures which are called the various submanifolds on them, spaces that like defects inside them, which are what they call associative or quasi-associative submanifolds in them. So these are a bit technical, so I won't go over the detail of them, but there's a tremendous amount of progress that has been taking place, and it's a very healthy interaction between physicists and mathematicians, which are part of these collaborations. trying to construct these spaces, trying to understand what they mean in the physics language, and back and forth between them. And let me just flash their papers, but I don't expect you to read it, so I'll just go very quick over these. They're doing good work, anyhow, so that was the main point of that transparency. But let me come back to the main question I want to talk about. Studying these manifolds and similar manifolds, we have to come up with what distinguishes the landscape of possible good theories, the effective theories which are good, versus the swampland, the bad ones, the ones that can never arise no matter what you chose as the middle space there. So the answer is we do not know them all. We do not know what are these criteria exactly. I wish I knew. I wish I could say, oh, you give me a theory and I will tell you immediately whether that's possibly can arise or not. We have evidence that the finite set, we have evidence that it's going to be very hard to get them. What exactly these conditions are, we do not know. So what do we do in this way? Well, what we do is, since not all of them are possible, we look at some of these observations can be captured by the ones that we actually construct. We look at principles that say, oh, look, you look at this set and that set and that set, they seem to all have a specific property. Could that property be beyond the examples? Could you experiment from these examples, extract a bigger principle, which tells you, oh, this cannot happen. This is it. And then how do we believe this? If you just looked at the examples, maybe you miss some examples that violate that. If we can relate those observations that we do based on some examples to a principle of physics which is beyond string theory, for example, the properties of black holes or something which has nothing to do a priori with string theory, and say in what sense does it make in that context, then we can begin to believe it more. So we can bring more and more evidence. This won't be a proof of these conditions. It will be beginning to get more evidence. So these ideas, so these principles that we have learned, I will try to review them, and these can lead to some specific predictions for our universe. That, okay, we don't know which one of them you're at, but no matter what you want to be at, this is not possible, or that is not possible. So this, if you see this particle, you better see another thing, and so forth. So there are these kind of predictions that we want to see what we can extract in the context of string theory. So the aim of my talk is to present some of these criteria. What are these criteria? And what we have discovered, and explain their motivation and what are the consequences of them. So before I do that, I want to give you some basic facts, which has nothing a priori to do with string theory. This was some of the properties that I'm telling you about was understood before even string theory came to be studied. And this is some properties of black holes in the context of a quantum theory and first classical and then quantum theory. So if you fix a particular charge, electric charge, let's say Q, and a particular mass, let's call it M. So for a given charge Q and a given mass M, you can ask, could you have a black hole which has that charge and that mass? Well, it turns out that if you choose the mass of the black hole to be sufficiently large compared to charge in some units, in what we call the Planck units, if mass is bigger than charge, there's always a black hole which does it. You can write solutions to Einstein equation, which are what we call black holes, which have a mass bigger than the charge. There are extreme cases where the mass can equal the charge, and that we call extremal black holes. But there's nothing less than Q. So the mass is always bigger than or equal to charge. You cannot have a mass of a big fat black hole which is less than the charge it carries. The mass is always bigger than or equal to charge. The next fact about black holes is that they have a horizon. They have a region, what we call the event horizon, which if anything crosses that inwards towards the inside the black hole, it cannot get out. So it's a one-way street. And black holes have thermodynamical properties. This is what Bekenstein and Hawking discovered. In particular, they carry entropy. And the entropy turns out to be related to the geometric property of the black hole, namely, this is the area. The entropy is the area of the horizon of this sphere that you cannot get outside, divided by 4 in the fundamental units of physics, which is the Planck units. So this has been known for a long time thanks to the work of Bekenstein and Hawking. Entropy in this case means that you have some microscopic states. There must be at least e to the s. There's a prediction that there's e to the number of s e to the area over 4 number of states. So when you have a fat black hole, that means there's a huge microstates of this black hole expected, despite the fact that Einstein theory gives you only one solution, which you might have said the entropy should be 0. Quantum effects that Hawking discovered, just semi-classical effects, predict that no, there should be a huge number of microstates, and they go like exponential of area over 4. And this is the picture of the event horizon of the black hole. And actually, I should have probably shown a picture of an actual black hole that was taken recently. But anyhow, so but anyhow, there's this the red region is the event horizon, and the number of state is exponential of the area over 4. This is the Hawking's formula. The other fact I would like to remind or review about is the black hole evaporation process. Even though nothing comes out of black hole, as I said, classically, Hawking discovered that black holes radiate due to quantum fluctuations near the horizon. So gradually, the horizon of the black hole evaporates, and particles come emitted out of that area. The black hole has a temperature, and this gradually makes the black hole shrink, loses its mass by this radiation, and at the end, it loses all its mass and it's gone. So the black holes actually evaporate in this quantum way. So at the end, nothing is left. So these are some of the basic facts we know about black holes, which has nothing a priori to do with string theory. It's arguments based on consistency of quantum gravity, which Hawking already studied and Bekenstein in 1970s. And string theory, being a quantum theory of gravity, better be consistent with them if it is a constant theory of quantum gravity. So these facts are beyond string theory in a sense. So now I will give you some of the criteria that we think are there for consistent theories that can arise in a good quantum theory of gravity. The first one is that in physics we can have symmetries, continuous, discrete, and all that. It turns out that in a quantum theory of gravity, you cannot have symmetries unless they are what we call gauged. And what that means, gauged means is, for example, suppose you have a rotation symmetry around the circle. If you go around the circle, that's a symmetry. Now, it turns out that symmetry can be gauged or ungauged. If it's gauged, what that means is that you have electric charge with the gauge field, the electric field sticking out of the particle, which carries that charge. So those can appear. So those are what we call gauge symmetry, that they have a field emitting from them. If they don't have a field emitting from them, it's just counting 1, 2, 3, 4, counting the particles, that we call global charge. Quantum gravity cannot accept global charge. They are not allowed. You can only have gauge charges. So if you have, for example, electron, you say, I have 5 electrons or electric charge, it's because there's a gauge field, electric field in this case, which is related to it. The second criteria is that all the possible charges that you can imagine is allowed and appears in your theory. You cannot say, I have some electric forces around, but sorry, I don't have electron with with unit charge, but I only have even charges, not odd charges. You will have to have all possible charges. You cannot have gaps in your charges. So you have to have all of them integrally quantized, beginning with the minimum allowed quantized one. The third criteria I want to review is that the range of fields. Now, these fields are parameters which classify your theory, the fields that we have in four-dimensional physics, like Higgs field and other fields. The range for these fields, should be finite. That is, if you have infinitely long range one, you get some bizarre property that I will mention. The next property is that the theory must admit higher dimensional objects, as in string theory, like membranes or strings, and I'll try to explain what is the relation between these criteria. Why is it that string theory wants to have extended objects? It turns out to be it's related. The principle of 4 follows, it turns out, from 3. So we can relate these properties together. The fifth one is that gravitational force, is always the weakest force. In our universe, that's true. If you take 2 electrons, they have electric repulsion. If you put them next to each other, they repel 2 electrons. But they also attract each other due to the gravitational attraction. They have mass. It turns out that gravitational attraction is far weaker than electric repulsion. And that is, we claim, true for any consistent quantum theory of gravity. You could have contemplated the electric charge to be weaker than the gravitational attraction, but that is not allowed in a consistent theory of quantum gravity. And then there are consequences for cosmology and dark energy and the fate of our universe that I will at the end mention. So only gate symmetries are allowed. Why is it? Why can't you have some global symmetry, like you count particle 1, particle 2, particle 3? What's the problem with that? What's bad about that for gravity? Why doesn't gravity like to be able to count? What's the problem? The problem is this. You take a black hole, and you start throwing these particles 1, 2, 3 in, and the thing is, you don't have any access to the inside the black hole. So once you have thrown them in, and then there's no electric field coming out of them, there's no way telling what is inside. But according to Hawking, it's going to evaporate the black hole. So at the end, the black hole diminishes in size and disappears, and you would lose the charge that you put in. So you lose that count. So whatever you thought you were counting, if they went to the black hole evaporation will kill that charge. That means there is no conservation of that charge. You lose that. The only way you can maintain it is if there's some field coming out. Like if you throw an electron inside the black hole, the electrical field comes out of the horizon of the black hole, and so therefore you see an electrical field out of the black hole, and you can see, I can count. There's one electron or something with negative charge inside there, even though you don't have access inside the black hole. And so black hole will preferentially emit charged particles to get rid of them, and so you can see them from the outside, so it's perfectly fine with the conservation of the electric charge if there's electrical field emanating from them. So that's basically the idea. The charge goes inside the black hole, and if there is no electric field coming out and the black hole disappears, so does the charge, and therefore the charge is not conserved. So there's no global symmetries in a quantum theory of gravity. The second criteria is that all the charges appear. If you have an electric field, and if you ask, can I have not the electron, but double the charge of the electron and 4 times, but not the odd numbers, could that happen? The answer is no. Why is that? Again, it has to do with black holes. Namely, pick a charge. Pick any charge you want. There is a black hole with that charge. There are many black holes with that charge. We can't solve the Einstein's equation. And you say, so what? Well, according to Hawking, it tells you that not only there's a black hole, but there are this many of them, e to the exponential a over 4, e to the a over 4 of them with that charge. And you can do it for any charge. Therefore, all charges must appear thanks to the entropy of a black hole. So again, black hole tells you, you better have these objects. It better be in your theory. You cannot ignore them. So as you can see, these general arguments of black holes suggest these. But thankfully, these are also consistent with what we have learned in string theory. So if you look at string theory, all the examples we know are consistent with these principles. So that's a good sign that we're having a correct theory. So in the next criterion, the finite range for the fields. So a field is like a function in space, like what we call like Higgs field. So you think about this phi as a function in the space, but you can say, what value does this function take? This field, we call it phi. In principle, if you just have one of these functions, you could have a real value, so any value from minus infinity to plus infinity. It could take any value. What's the problem? Well, it turns out that if you start with any description of your 3 plus 1 dimensional physics, if you move too much in this parameter space, in this field space, you find, and this field space, the distance that you move on, is characterized by a scale which is the same as the Planck scale. So in the fundamental units, if you move 1 unit, then it turns out that you get beginning to get light states in the theory, and invalidates your 3 plus 1 dimensional description. So let me say it a little bit more clearly. What happens is this. These scalar fields in the geometry language correspond to the sizes of these manifolds that we were talking about. So you say, okay, so suppose I take the metric and rescale it. I take this space and make it bigger and bigger and bigger, this tiny thing that we were talking about, this compact space in the middle. Suppose we make it bigger and bigger and bigger. What happens? It turns out that when you solved for the string states, you begin to get a tower of light states. The more you make the space bigger, the lighter you get for the states, and eventually you get so many light states that it tells you that the description you originally thought was describing your light state is not right. You're getting an infinite tower of light state emerging. So if you want to avoid this infinite tower of light state, you better stick to finite sizes. You don't want to change the shape of that space. So studying, for example, Calabria manifolds or G2 holonomy manifolds or spin 7 manifolds, all of them are consistent that when you try to change the shapes too much, change the sizes too much, you get a tower of light states. You solve the equations in string or properties of solutions to Laplacian or what describes the modes that you get, and you find that you always get towers of light states. And so this is captured by this picture. So if you move in what we call this space, in the physics language or math language, we call this the moduli space, the space of these parameters. If you move in this space, you begin to get light states when you get to the corners. So if you're moving from the middle to somewhere far away, you begin to get tower of light states. Extended objects. Why? Okay, so forget about string theory. Why should a quantum theory of gravity have to have extended objects? Isn't it bizarre? You start with a point particle and somebody said, no, I don't like that. There's nothing seems to be bad about points. What's the problem? So can we understand what goes bad with that in that language? It turns out that this is related to the principle that you cannot move arbitrarily large distance without your theory breaking down. So why is that? Well, suppose in any given quantum theory of gravity, suppose you're given any theory, and imagine taking it on a circle, like you take a periodic boundary condition for one of the directions of your space, thinking of it as a circle, and see what happens if you take the size of the space to be big or small. If you take the size of the space, let me call it the radius r of the circle, to be e to the phi, so I view this phi as the scalar I was talking about. So if you take the radius to be big, you get light states. What are the light states there? Well, these are just the harmonics that you go around, the sinusoidal waves that you can choose on the circle. The bigger you make them, the lighter in energy they are. So you begin to get the light and light state just by making the space big. So that's an example of how you get these tower of light states. But suppose somebody says, what happens if you actually make it shrink it? So if the value of r goes to 0, it means phi goes to minus infinity. So suppose I take this circle and shrink it down. These harmonics become very energetic, so there is no problem with them. They're just very massive. So what is the problem in this case? Well, I said that you better get a tower of light states. Where are those? The only thing we are doing is that we are identifying one side of the space to another, where the size of the identification is getting smaller and smaller. The only way you can get a light tower is that if you have an extended object, which stretches from one side to the other, like a string or like a membrane. So if you have such an object, as you shrink the space, if you wrap it around it, since the energy it has is the tension of the string times the size, when you decrease the size, the mass goes to 0, or the energy goes to 0, and you get the tower of light states. So you need an extended object for the quantum theory of gravity to be true. So this is the two limits I talked about. R much, much bigger than 1, you get these harmonics, and phi much, much less than 0, you better get something like an extended object. So this is the only natural mechanism, as I said, is describing it by extended objects. So let me talk about why the gravity is the weakest force, or what's the explanation for that. So as I mentioned, if you take two electrons and put them next to each other, there's an electric force between them, given by this red arrow. They repel each other, given by the square of the electric charge times the distance divided by distance squared. This is the Coulomb force law for electric charges. And if you take the mass of the electron to be m, there's a gravitational attraction given by these blue arrows, which is equal to the mass squared of the two electrons divided by the distance squared. So as you can see, the distance, if you take the ratio of these forces, the distance is the same. So it really depends on which E is bigger or M is bigger to see which one wins. In our universe, the mass of the electron is less than its charge. Much, much less than its charge. So the gravitational force loses by far. And the claim is that this is always the case. So why is that? Well, again, black hole explains it. Black holes explain the weak gravity conjecture in the following way. You take a big black hole in the extreme case where the charge equals to mass. This is the biggest the charge you can have for a given mass. And you ask, what happens? We said, well, this should evaporate. So how it's going to evaporate? Well, it should evaporate by emitting charged objects. So you take a tiny charged object with some charge and small mass. So small charge q and small mass m. So if it emits that by quantum effects, the black hole loses charge by conservation of charge and conservation of mass. So the charge goes down to Q minus, capital Q minus small q, and the mass goes down by m minus q. Now, if you started with q equals to m, if you want to maintain that q is always smaller than capital M, the capital Q is smaller than capital M, for this to work, you must require that the small m better be smaller than q. So in other words, the elementary particles that you're emitting are the opposite in terms of the black hole condition. Their mass is less than the charge, even though the extremal one, black holes, the regular black hole, is the opposite sign. And this is simply just the conservation of this evaporation process. So this gives you an explanation of why in the context of string theory, we should have gravity as the weakest force. So the last topic, which is actually potentially the most exciting one, is the connection between cosmology. What do these conditions, what do these things that we are learning from string theory have to do with cosmology? Can we learn anything about the observed universe? Well, so let's review what's the basic story for cosmology. Well, we don't know much about the very early time. Maybe there was inflation, maybe there was something else, but at any rate, we know at some point we got this very homogeneous background with slight perturbation, and that evolved after that to our universe. The seed of it could be inflation or something we don't know yet. And this is beginning this point onwards is what we call the Big Bang, cosmology. And the universe expanded and cooled off, and it gives you all these structures that we observe today. It's a very well-tested paradigm, and it is beautiful experiments that have been done already to confirm this picture. So there's very little doubt that the general picture seems basically right. And the time evolves. In this picture I'm drawing to the right. So you might ask, how long has it been? Well, it's about 13.7 or 8 billion years, or some time of the order of 14 billion years from the beginning till now. Okay. Well, will it end? Might be curious about that. It's an existential question. How long do we have? Hopefully by the end of this lecture we're still around. Do we know? What do we know about the fate of our universe? Is it going to stop, or is it going to keep on expanding? Well, I have a news for you, perhaps. The only universes that last forever have a special property called supersymmetry. All the other universes that we have been able to construct using string theory, which don't have this property, are unstable. One way or the other, they go away. They disappear. So I'm assuming that you're all hoping we are part of this supersymmetric universe, otherwise we would disappear. So first of all, what is supersymmetry? Supersymmetry tells you that for every particle, here let's say these green particles is one side, there's another shadow particle, these yellow particles, which have the same mass. This blue is the energy scale or mass scale I'm drawing, with the same charge. Every property between them is the same, except their spin is slightly different. The spin of one of them is slightly higher or lower than the other one. Otherwise, exactly the same property. Somehow, this translates to an amazingly powerful property of the physics, which I don't have really a time to talk about. But actually, the special holonomic collaboration is precisely the kind of situation where this arises. So precisely those spin 7 or G2 or Calabria are the ones which are the good universes that if we had those, we would live perhaps forever. We'll give you supersymmetry in particular. But you can ask, we have learned quite a bit about supersymmetric theories. You can ask what kind of things we have learned. If you ask about the dark energy in the supersymmetric theory, we learned that the dark energy can be 0 or negative, but never positive. Oops. Dark energy can never be positive in the supersymmetric theory. And moreover, you should have for every particle another particle. For electron, there must be another shadow particle, what we call selectron. We look for it. The same mass of electron, it doesn't exist. Okay, there goes supersymmetry. We don't have supersymmetry, at least in the energy scales that we have in our universe, as part of the theory we live in. Therefore, string theory landscape would predict we are not going to last forever. Okay, we should pick our poison. Which way are we going to go? we are not, the whole universe is going to disappear, we think, because we think in the context of these swamplands, even though you could have imagined a theory which would have lasted forever, precisely because it's not one of these special holonomy or Calabria or whatnot, we are going to go away, okay? What way are we going to go away?
But you had this thing that required it to be compact, not compact.
If it's not compact, the Newton constant will not be finite. It will be zero. So to have a gravitational finite Newton constant is related to the inverse of the volume of that. So in other words, if you do want to have finite Newton constant, you want compactness. So how long do we have? Okay, we know we're not going to last forever. How long do we have, and what's our fate? How are we going to disappear? I'm not just talking about the Earth, by the way. I'm talking about the universe, the whole thing. So our universe has dark energy. That's one of the most fundamental discoveries, I would say, of the past few decades, is precisely this understanding that the universe, there's a dark energy filling everywhere. We have measured a certain amount of energy permeating the whole space. This is remarkable. But it turns out there's more to it. To energy scale, there's a natural time scale you can associate to that energy. And if you measure that energy, it comes out automatically from just that measurement of that energy here. You can measure a time. You might think that time might be something special because it might be telling you something about that energy and our universe. You ask, okay, what is the energy what's the time you might associate to this dark energy, which is given in the fundamental unit by something like 1 over square root of that energy. Well, let me just show you what it is. Well, our universe has lasted till 10 to the 10 years. Now it's about 14 billion years. And the time scale you get from this 1 over h is roughly around the same number. It's 10 to the 11. Oops. It's very, very too close for comfort. What's going on here? Why is the natural scale that you get from this dark energy close to our scale? Is it trying to tell us something? Well, physicists have labeled this, among other things, what's called the coincidence problem. It just happens, there's a time scale comes out of dark energy, and we happen to live in a time which is the same scale of it. Not necessarily satisfactory explanation. So, are we going to go away? No, well, let's see. Before we get carried away, let's come up with other pictures that we know. We do know that even if the universe doesn't disappear, the protons we are made of will disappear. At least that's our current understanding of what we expect in grand unified theories, which we think is happening in our universe. And the protons will decay 10 to the 35 years. Well, that's long away, but this is more worrisome. What's going on here is closer to us. So could this be the signal that something is happening like in 100 billion years? Well, how do we get dark energy in the context of string theory? The way we think of getting it is that there is a field, like this variable I call phi, and there is the energy potential as a function of this field, and it has a minimum, and the value of the minimum is a positive value, and that value is what we call the dark energy. That's one picture of how you get the dark energy, or what's called the cosmological constant. So in other words, you naturally will want to reside at the minimum of this potential with a positive value of the energy, and that's where it is. So one can easily contemplate having the de Sitter space that we live in. So you may think, what is wrong with this? We can be forever in that minimum and we won't decay away. Who's trying to throw us out? Well, it turns out that's the nature of it, that in string theory, we don't have any example of this situation. Anything we construct, we can try to construct things like that, and people have tried to construct, but no matter how much you try, there are places in the potential that actually go down below this, all the way to zero. So there's no way you can have a stable one. At the best, you can hope for some situation where this tunnels through. So we will never have a stable de Sitter space. And then you can ask, what is the rate at which it can decay? To tunnel through this barrier, could it be that we are in the minimum and then we're going to tunnel through this to the other side, but it takes a long, long, long time, much longer than what I have told you about 10 to the 11 years. It could, in principle, if the height here is sufficiently high. If this is sufficiently up, it will be difficult, or if this is sufficiently wide and high, it will be hard to tunnel through it. And therefore, we can be very long-lived, and we don't have to worry about it. Our grandchildren and so on all will come and go, no problem. But what it dictates, do we have that choice? Well, you can write an effective theory which looks like that, but do they belong to the swampland, or do they actually exist as quantum gravity systems? We are not at the liberty to draw our favorite function. We do not know which ones arise, and we cannot just say, I like this one, why not? We don't have that liberty, so we just have to see what are allowed possibilities. There's another possibility, in fact. It is the possibility that you're not at the minimum of the potential, and you're rolling. Namely, you're at the value of some field, some value, which you call the dark energy, the value of the height here, but the value of the field is going to evolve to the right here as the potential goes down there as the time evolves. So it could be that you're rolling. And it turns out that you can have, if you have sufficiently shallow or low-sloped potential, this is perfectly consistent with observational cosmology. So we could be either in this situation or in the other situation. So we don't know yet. Either at the minimum, at the bottom of the potential, or sufficiently flat, rolling potential. So there are arguments about why this scenario might be bizarre, the one I'm just telling you about. The reason is that if a parameter changes, if the value evolves, this will couple to things which we see and measure, like electric charge and this and that, and you can measure whether or not there has been changes or variations of, for example, the electric charge of the electron since long ago till now, because we have observational data from how the faraway galaxies or whatnot work, and you can bound it by how much it could have changed, and you find very strong bounds that doesn't change much, which would be inconsistent with this picture unless it's really, really, really flat. So people begin to say, well, this doesn't sound very likely then. So that's one scenario. But actually, that's not necessarily a good argument, because it could be that this field that I'm talking about is coupling to the other things that we haven't seen, namely the dark matter. The dark matter is a part of our universe, we believe, but it's hard to see direct evidence for them other than their gravitational impact. And this field itself could be not part of our sector, but part of the other sector, part of dark matter. So it could belong to them. And therefore, it will interact strongly, perhaps, with the dark matter sector, but not with us. It is a very natural possibility, in which case those arguments would not be good to rule these out. But there is another strange feature of quintessence models. The value of the potential, which gives you the dark energy today, in fundamental units of physics is 10 to the minus 122. Really, really small number, which is why we originally misled theorists to think it better be zero, otherwise why is it so small? It turned out to be small for whatever reason. Now, but also the funny thing is that if you want that small v to get no inconsistency with cosmology, you also need the slope, the gradient of the v, the slope of it also to be small. So you are double fine-tuning. You are saying not only the value is small, the slope is small. Okay, you could say I will live with one fine-tuning, but not two. Okay, that's one of the reasons people don't like this kind of thing where you actually have also a rolling potential. You say, well, minimum makes sense, it's kind of a natural thing, but having a very fine-tuned small potential and the small slope sounds bizarre. Unless there's a good reason that the slope is proportional at the minimum to the value of the potential. In which case, these are not double fine-tuning. One dictates the other. There's a minimum for one of them. And it turns out, in string theory landscape, we often encounter situation where you take, for example, these manifolds, like special holonomy manifolds, and put potentials on them, you find the gradient is of the same order as the potential itself. So that means that if you fine-tune one of them to be small, you have already done the other one automatically, so you don't have to worry about it. So it's not double fine-tuning. So therefore, this raises the question or whether or not you can have the following possibility, that the slope is always bounded away by some constant times the value of the potential, because this seems to be the case for all the examples we understand weakly in string theory. Could this be a condition for swampland with a finite range? Well, you can pass this through various epochs of past situation, like how the inflation will fit with this picture. I won't bother you with the details of the parameters, and it seems like you can't fit the inflation with this idea that the slope of the potential is bounded by the value of the potential, as long as you allow some leeway about what are the parameters in the inflation, and as what is the range of the field. Namely, it should be 5 units in M Planck in this kind of picture. And then you can ask whether or not you can have a potential which looks like which has a small logarithmic slope, which means it looks like e to the minus constant times phi. You find if the constant is less than 0.6, 0.5, and so on, you can fit it with the observed cosmology today. So the perfect cosmology today will be agreement with a situation where you have a slope for this potential. And the future, the question is, well, the future, as I said, there are two possibilities. Either there's this conjecture that the slope is always bigger than the value of the potential, in which case this will not be even allowed. So namely, you cannot have a metastable, you cannot have a situation like this which tunnels away. And this is, in some sense, you could say good, because why would it explain that the value of the energy, the time scale you get from this dark energy has anything to do with the age of the universe? What explains this coincidence problem? If it was like this, it could be much, much long-lived, and what we happen to live in this epoch to measure the dark energy compatible with the age of the universe in this way is bizarre. Unless there's another possibility. The other possibility, which is now also being studied, is perhaps this kind of situation that I'm just denoting here may arise in string theory as long as it's sufficiently fast decay. Sufficiently fast decay means the time scale for it is of the same order as the time scale that the dark energy gives, this 1 over square root of E. So there are two different competing possibilities that one we are studying, and we are not sure which one. So either we are going to be short-lived of the same scale as the dark energy, then that comes as one of the swamplands, or it's just forbidden. You cannot have this situation. In either way, you can follow the conclusion of what is the lifetime, future lifetime of our universe, how long do we have, and it turns out it is within 10 to 100 times we have already had in the universe. That is, the age of the universe is no more than 100 times of current age. From these pictures, we are led to the picture that the age of the universe, the finite, the upper bound for the lifetime of the universe is no more than, if we call our current universe 1 year old, no more than 100 year old. We can give before the whole thing disappears. And you might ask, okay, what is the signal of this disappearance? Well, if you're in this situation, what will happen is that you will suddenly decay. It's like a bubble of this. Some part of the space, maybe some faraway galaxy, suddenly moves from here to the other side, and it starts expanding to this new region because it has lower energy. And this looks like a bubble which kind of like washes out all our universe, erases it, and replaces it by a new universe. And this bubble will come and take over us, erase everything. But it comes, don't worry, it comes with the speed of light, so we won't notice a thing. It just wipes the whole thing out. That's one possibility. So we will not have a time to react to it in any way. Or the other possibility, you might like the other possibility a bit more. The other possibility is that you might be rolling, and what happens that as you roll, you get, because as I told you, when you move in the field space, when you move, you get a tower of light states. So what will happen if you're in this scenario? You get gradually tower of lighter and lighter states, and what we are made of is going to decay to this other matter. Not that the universe is going to slip under your feet, but well, maybe the object you are made of will go away to something else. So there will be a phase transition of some kind, and you can estimate the phase transition. And again, as I said, it's the same scale, 10 to 100 billion years. So, 10 to 100 times the current age, which means 100 to 1,000 billion years. So this is already quite remarkable that from these kind of ideas from string theory, we are being led to statements about what could possibly be the ultimate age of the universe, final lifetime of our universe. And the fact that you might get this tower of states and this light tower of states being part of the dark sector seems to be compatible with some of the recent observations in cosmology, which is still being debated. It's not settled yet. So the recent measurements of the Hubble constant for present time has a slight tension with the standard model of cosmology, what they call lambda CDM. So the value that people measure is slightly higher for the present value compared to the value you would have predicted based on earlier data, for example, from CMB that people have measured. And this gives you a model, and indeed it turns out in these kind of models where the dark matter has a mass which is actually going down when you're getting this tower, it improves the fit by about 2 sigma in terms of observations, but it doesn't resolve the tension completely, but it gives you a little bit better fit. In fact, next generation observational data is coming from various different quarters, including one which will be coming from Simon Observatory, and these will clarify what is the value of H naught, whether there's a real tension or there's just a systematic error maybe somewhere in the experiments, we don't know. So it'd be crucial to find out what it is. It has, as you can see, strong bearing about what could potentially be the fate of our universe, the picture we have about what could be happening to our universe in the future. And so this will be extremely interesting to find out what the prediction for these values might be. So this I just told you that the lifetime you would get is something of order of 30 times of this Hubble scale, but numerical computations from various models, when you fit to the data, it gives you these kind of values. So the future is finite, I'm sorry to tell you, but it's long, it seems, so you don't have to worry immediately. We have a few more generations to go at least. But it will nevertheless, the swampland idea, sorry to say, will come up with a prediction that's finite, nevertheless. It is going to come to an end, but nothing to worry immediately. So let me conclude. So the ideas coming from swampland are beginning to get sharpened. We don't have the full story by any means, and we're just beginning to gather little pieces of evidence of what they are. Studying compactification of string theory on these special manifolds are one of the key tools which give us insights about what are possible. And people are pushing that as a way to gain insight about these deep questions about what is the fate of our universe. So with that, I think I'll stop. Thank you.